So this type of element will be used for plane stress. So if I have a case, if I'm working in the XY plane, and I have a part that is subject to loads that are also acting in the XY plane, and this part is relatively thin. Let's say I have here the traction surface forces TS. Then I can model this structure using these CST elements. So on step number 1, we are going to select the element type. And we are going to go with a basic triangular element. Why triangular elements?
Still, it's in 2D.
Yeah, it's into. So why not rectangular?
3D.
Well, I'm looking at 2D, right? Even in 2D, it is easier to get a closer approximation to complex geometry when you have that triangular element, right? So remember, this is an approximation when I'm filling in, right? So this is something to keep in mind, that triangular element, so that if we have boundaries of irregularly shaped bodies may be closely approximated okay, so that's one reason. And the second reason is that the related expressions are relatively simple. Relatively. So what we're going to do next is to discretize the plate. So we're looking here at a plate and a case of plane stress. So I can come to my plate. Let's say we're going to break it and fill it in with rectangular elements. So I'm going to be looking here at coming up with a mesh. So you see here how I used triangular elements to approximate my boundaries or my geometry. And typically, from what you're seeing here, we can count the elements. So I don't really have hundreds of elements. So what I did here when I discretized my plate, I used a coarse mesh generation where with this coarse mesh generation, I'm using few large elements. I'm not using a very small element. Okay. Now, if I look at this triangular element, like the shaded green one, I have something like this. So we clearly have 3 nodes, at least, right, for this element that we're going to derive. And we have 2 degrees of freedom per node. We are working in the XY direction. We have translation for X and Y translations that we are going to refer to as U and V. And for each of these degrees of freedom, I'm going to use a subscript I, where if I use I, it would be for node I. If I pick a generic element, just if I'm working in the X, Y plane, and I just have any shaped element, like this. I'm going to label my 3 nodes as I, J, and M. And for consistency, we are going to use a counterclockwise system of labeling the nodes. So you see when I'm labeling my nodes, I go like I, J, M. And when I am discretizing, each of these nodes is going to have a known coordinates in the XY plane. So for I, I'm going to have an XI and a YI. For J, I'm going to have an XJ and a YJ. For M, likewise, I'm going to have XM and YM. So the formulation is based on counterclockwise system of labeling of nodes. And this consistent labeling procedure is necessary, right? So we have to remain consistent. Okay. Consistent labeling procedure is necessary. All the ordinates X, I, YI, XJ, YJ, XM, and YM are known nodal coordinates. At each of these nodes, I'm going to show my 2 degrees of freedom. Translation, UI in the X direction, VI. Okay. At J, I'm going to have a U, J, and a V, J. At M, I'm going to have a U, M, and a VM. So nodal displacements may be described by a displacement vector using a column matrix, where this D is equal to 3 submatrices: the displacement at node I, 2 of them, displacement at node J, and the displacement at node M. I can expand these matrices and write a 6x1 by putting here UI, VI, UJ, VJ, UM, and VM. So we have selected an element, we discretize the structure, and we define the element coordinates and the number of nodes and the nodal displacements. Step number 2. Displacement functions. Why functions? With 1D elements, we had one displacement function that would give us the displaced state, because usually it was like U or V and that's it. But when I'm working in the XY plane, I'm going to have displacements in the U as well as the V, right? And we are going to use, of course, this U function is going to be with respect to X and Y. So it's going to be a function of X and Y. And as we have 6 degrees of freedom, we are going to have 6 nodal displacements. We're going to have 6 unknown parameters to solve for. So I'm going to have U of X, Y, as well as V of X and Y. If we are going to have 6 parameters, I can express U of X and Y as A1 plus A2X plus A3Y, and V of XY as A4 plus A5X plus A6Y. So these displacement functions describe the displacements at any interior point that has, of course, X and Y coordinates. And the linear functions we're using ensures compatibility. If I want to use a general displacement function, C, I will call here that C is equal to U of X and Y and v of x and y, where this is equal to a1x plus a1 only plus a2x plus a3y, and v of x and y is equal to a4 plus a5x plus a6y. Now these may be written as two matrices where multiplied by each other, where I have all my parameters A1, A2, A3, A4, A5, and A6 here. And here I'm going to put my equation. So I have here one A1, and then I have an X, A2, and I have a Y, A3. I have 3 zeros after that. And on the second row, I'm going to start with 3 zeros. Then I have 1 X and Y. So this is another way to represent the general displacement function of C. Now, we want to obtain this A's value. So to obtain the A's, we are going to substitute the coordinates of the nodal points I, J, and M. Right. So I'm going to have a UI where I'm going to use the U function, but I'm going to substitute for xi and yi. And I'm going to get here a1 plus a2 xi plus a3 yi. I'm going to get uj equal to u of x, j, and yj. That is equal to a1 plus a2 xj plus a3 yj. um equal to u, and I'm going to use xm and ym, and I'm going to get a1 plus a2 xm plus a3 ym. vi equal to v of xi and yi is equal to a1 plus a2, a4 plus a5 xi plus a6 yi. And vj, I'm going to use xj and yj. So I have a4 plus a5 xj plus a6 yj. And finally, vm, I'm going to use xm and ym. And I have a4 plus a5 xm plus a6 ym. So we're going to solve for I have to say here, of course, that these are nodal displacements, UI uj, um, vi, vj, vm. So we're going to solve for the a's expressed in matrix form to make it easy. So I have here ui, uj, um is equal to. So I'm going to take the first three equations and I'm going to write it in matrix form. I have A1, A2, and A3. I have here 1 xi, yi, 1 xj and yj, 1 xm and ym. So if I consider this to be an X matrix, I can solve for A if I can find the inverse of X and multiply it by U. So we can use the method of cofactors to find the inverse of X, where this X minus 1 is equal to 1 over 2A multiplied by alpha I, alpha j, alpha m, beta I, beta m, beta j, beta m, gamma I, gamma j, and gamma m. Where 2A is equal to xi times yj minus ym plus xj times ym minus yi plus xm multiplied by yi minus yj. So this is the evaluation of the determinant of X, right? So 2A is equal to the determinant of X. 2A is equal to the determinant of X. The alphas, betas, and gammas, these are the elements of the cofactor or the transpose of the cofactor matrix that I'm gonna share with you next time when we continue. So we're gonna stop here and we're gonna continue next time. Thank you.